Okay, so we talked about localized stress. Let's talk about some localized strain now. So, uh, yeah, strain in general, uh, that's referring to the intensity of the localized internal deformation. So, um, it overall, like if you have a bar, and you're pulling on it, the strain that you cause by like the average strain of of the bar in the direction that you're pulling it is just going to be a kind of a ratio of the original length of the bar divide sorry the new length of the bar divided by uh, uh, sorry the change in length of the bar divided by the original length of the bar. Strains caused by stress when we induce this when some sort of load is applied to it, uh, then it will induce a stress. If that stress is below its yield strength, then the strain that we cause is going to be linearly proportional to the stress that's applied. So it's most of the calculations in this course are kind of based upon the assumption that we are staying within that linear elastic region. So we have the concept of Poissons Ratio. I'll post another video that explains it a bit better than I can because it has nice animations and I don't. But essentially, when you stretch something out, it it has a tendency to kind of contract in the directions that you're not pulling on it. So if I pull on a bar, it's going to increase the length of the bar, but as a result, the width and the height of that bar are going to decrease. Essentially, like you can think of it as it's not exactly the same but you can think of it as you've only got a certain amount of volume to work with um, in terms of the the physical volume of the bar. So when you stretch it out, it shrinks down to try to keep the same volume. And it doesn't actually work out for the vast majority of materials to be matching the exact same volume, but the principle is somewhat similar. So when we look at this, when we're calculating our strains in a particular direction, that's going to be a function of the kind of the induced stresses in that direction, divided by the Young's modulus, of course, and also uh, the Poissons ratio and the induced stresses in the opposite direction. So don't forget your negative sign here, because those are generally going to be causing when you're pulling in one direction, it's causing the other two directions to contract. Also got our handy dandy shear strain here. So shear strain, thankfully, thank God, does not have kind of a Poissons ratio-like effect. Essentially, what we're looking at when we're talking shear strain is we apply some sort of shear stress to the element, kind of if we're pushing on the cube on the sides in a manner that's going to like this, and then on the other side like this and like this, that's going to cause it to kind of want to distort so that the angles change. So like the angles on this face, the angles here are going to increase, the angles here are going to decrease. And essentially the strain that we're defining is going to be based upon how much the angle changes. So we're keeping this in radians. So if the original angle here was 90 degrees or pi over 2, and then we distort it so it looks more like this. And this new angle here, it's going to be pi over 2 minus gamma. So again, depending in this instance, assuming that this is the x direction, this is the y direction, this particular strain would be our xy strain. Now again, the definition is such that that is going to be positive when, so we're starting out with a cube here. This is going to be positive if these angles here get smaller and these angles here get bigger. And that's essentially just so that we can kind of keep in mind that we want our strains to be proportional to our stresses. So if we have, again, an x, y coordinate system, and then if we have a positive shear stress in the a positive xy shear stress, and that means that we have on this front face here, on the positive x face, we have a force pushing in the positive y direction, and in the positive y face we have a force pushing in the positive x direction. And then obviously on the other sides of the cubes, on the negative x face, we have a force pushing in the negative y direction, and on the negative y face, we have a force pushing in the negative x direction. So if we've got positive shear, then we want that positive shear to result in positive strain. So that's why that would be why having something like this is going to be a positive shear, whereas something like this would be a negative shear. So like I said, thankfully we don't have anything similar to our Poissons ratio effect for shear strain. They don't affect one another, basically. Looking at the different looking at the different orientations or the different sides of the cube. That having been said, here's a good point where we've talked about Young's modulus. We've talked about our shear modulus. Our shear modulus is basically the shear strain equivalent of Young's modulus, denoted by G here. And we talked about the Poissons ratio. Only two of those things are independent variables. So if you know the Young's modulus and you know the shear modulus, you can use it to calculate Poissons ratio. If you know the Poissons ratio and Young's modulus, you can use it to calculate the shear modulus. And if you know your shear modulus and your Poissons ratio, although typically speaking, if you're given two values, those won't be the ones that you'll be given, you can use it to calculate your Young's modulus. You're almost always going to be given Young's modulus, because Young's modulus is the easiest one to measure. But anyways, So if you want to look up why that's the case, it has a lot to do with kind of the geometry going on in a when something gets distorted, but your textbook has the derivation. I don't want to get into the derivation there. You need to know that relationship. I don't expect you to. I expect you to be able to follow along with the derivation, but I don't expect you to necessarily know it. So also got thermal strain. So you got our objects. They're made of a bunch of molecules, molecules and atoms, and those molecules and atoms are, they're hyperactive. They're wiggling around in space and so on and so forth. They're bumping up against one another. The more we heat them up, the more they vibrate, the more they bump into one another. And when they do that, the more they do, the more they want to stretch out, right? The more space they want to take up. A bit of a simplification, obviously, but that's the key here is, generally speaking, increasing your temperature will increase the size of the object. So thermal effects will generally cause uniform expansion or contraction proportional to the change in temperature. Now, obviously, there's some materials where that's not the case. I think everyone's familiar with the notion that when ice freezes, it expands. I think the density for ice, well, density for water is at its minimum at, I think it's 4 degrees Celsius, somewhere around there. But when we're talking, that's due to kind of that's due to the kind of the polar nature of the water molecule. It doesn't really come into play when we're talking metals or basically any engineering structural materials. Actually, no. I'm not going to be that. I'm not going to state that statement quite absolute. The vast majority of stuff you're looking at expands when you increase the temperature, contracts when you decrease the temperature, for the range in which we expect it to be used at. We have this material property, the coefficient of thermal expansion, so typically denoted by alpha. That tells us kind of how much it's expanding, how much any individual bit is going to expand based upon how much the delta t is and the length. So typically speaking, this delta t is equal to alpha. Oh, okay, so small delta t is equal to alpha big delta t L is how this is typically reported. I don't like that because, for one thing, I kind of like to put things in terms of strain, so that we can plug it into, so that we can kind of make a big equation that relates how everything works. So one thing that, if we just kind of look at length here, people might be inclined to believe that it kind of only goes in one direction. That would be erroneous. When we add the temperature, it expands in all directions. So this cube here, it gets bigger in all the directions. So the essentially what happens is we are going to get a bit of strain induced that is proportional. We're going to get strain induced that is proportional to the temperature rise. So essentially, kind of we took this delta t, small delta t divided by the L. That gives us our change in length over the original length. hey, that's our strain. So strain at any strain before the temperature. Sorry, the strain that we get after the temperature raise is equal to the strain that we had initially, kind of based upon what else we're doing it, plus our thermal effects there. So, and everything, we can take all the things we talked about and we can combine them into one big equation, because we're going to need to understand how these things affect one another. So that allows us to build what we'll call the Generalized Hookes Law. So here what we're doing is we're relating how the strain in each of the three directions, like the normal strain, and then our shear strain in each, in each of the three orientations, is related to the stresses and our thermal effects. And of course, all of that comes into play with also our Young's modulus and our Poissons ratio. You'll note here that they didn't put G in here. And again, this is just a result of them only wanting to use the two independent variables. So if we took this equation here and solved for G, we're going to get this equation here solved for G, took that G, plugged it into here, and then basically solved for the strain as a function of the stress, then we would get this 2 times 1 plus our Poissons ratio divided by E term here. So essentially that's what's going on there. That they didn't, we don't want to use the multiple. We didn't want to use more than one. We didn't want to use 3 interrelated terms when we could just use the 2 independent terms. So, so we've got that. So we got this is what we're doing to the object. We're applying some sort of loads, and those loads are inducing stresses. We've also got our material properties, so our Poissons ratios, our Young's moduli, and our coefficient of thermal expansion. One thing about the coefficient of thermal expansion is, again, that is a value that you often look it up on a table, or you'll be told it for the problem whatsoever, and essentially that is a number that represents kind of like a typical response characteristic for the material over a certain temperature range. This thing is, technically speaking, temperature dependent, but that makes the math really complicated, and we tend not to want to have to deal with that. And it also tends not to vary all that much. So we typically kind of just report a single value for that and say it's close enough to accurate for our purposes. But there may be some cases where you might need to kind of have that as a function of temperature instead, in which case, again, yes, stuff gets complicated, a lot more complicated. So got the material properties, we've got what we're doing to it in terms of the stress we're applying. we got what we're doing to it in terms of the temperature rise. Again, when we apply temperature, it causes an increase in the volume, so it's kind of increasing the strain in the three normal directions. It doesn't cause it to distort at all. Like heating up a cube doesn't cause that cube to start to skew to weird angles. It just gets bigger. So it doesn't. The temperature rise doesn't have any effect on your strain levels. Sorry, your shear strain levels. So and then of course we can sometimes you'll be wanting to calculate your strain, and you'll know your loads. Sometimes it'll be the other way around. Sometimes you'll know the strain, and you'll be given a temperature rise, and you'll need to calculate what stress levels gets induced. Something like that can happen too, or you'll know the you'll have a known strain that this thing can expand to, and you have a known stress, and then you need to figure out what sort of temperature you change this thing can accommodate before the strain gets too high or something like that. It's you can work from one end of the equation to the other, and it all still works out. So that's how we get a nice big matrix that kind of allows us to interrelate all of those topics we talked about. And then, of course, once you solve for this here, you can take that and you can just throw it into a 3x3 strain matrix where you've got our X, Y, and Z strains for our normal strains, and then we got our shear strain in the XY, our shear strain in the XZ, and then our shear strain in the YZ. So again, similar to what we saw with stress, the strain it is a 3x3 matrix, but it's only 6 independent variables because these need to be the same, these need to be the same, and these need to be the same. And yeah, that'll be how I when you're expected to report the strain tensor, that's kind of the format that's going to be expected. So yeah, and then we'll the rest of the videos are kind of how to work through some problems involving this. So once we start slapping together temperature rises and so on, shear strain, strain constraints, or what have you. A bunch of different ways to tackle things. Right, and yeah, see you later.